Great. Well, thanks a lot for the invitation, Franco and organizers. Really appreciate it. I'm going to try and set this up appropriately. And let me know, does that look good on your side?
It looks great.
Okay, fantastic. Again, thanks a lot for the opportunity to speak today. And that kind introduction, Franco. I'd like to talk about a topic which is near to my heart, and also Franco's too. I'd like to recognize Anton Fritz Kokum and also Franco Nori for motivating and doing the theory behind this work with giant artificial atoms and waveguide QED. So by way of introduction, when we talk about atoms, whether they're natural atoms or the artificial superconducting qubits, artificial atoms, we're generally talking about small atoms. And what we mean by that is that the spatial extent of the atom is small compared to the wavelength of the radiation that we use to drive transitions within that atom. And when we talk about artificial atoms or superconducting qubits, we generally talk about a single qubit like this, and we attach it to a cavity or a waveguide in this case. And there's one point that we couple it. And when these are satisfied, we can use what's called the dipole approximation, where the polarization of the atom follows the field and then the transition occurs. Okay. So this basically is saying, look, it's a point-like atom. And if we look at, say, natural atoms, which are driven by optical light, a natural atom has a radius of about an angstrom. The wavelength is around a tenth of a micron to a micron. And so this ratio of the two is 10 to minus 3, 10 to minus 4. Okay, that's point-like. Rydberg atoms, even more so. The radius of a Rydberg atom is relatively large, so 100 nanometers or so, but the wavelength that we use to drive it now is in the microwave regime. And so this ratio is now 10 to minus 4, 10 to minus 6, so even more point-like. Conventional superconducting qubits are also point-like. They're rather large, 100 microns, but because we're driving them at microwave frequencies, again, this ratio is 10 to minus 2, 10 to minus 3, which is fairly point-like. So we'll call these small atoms. And in contrast to that, here we're going to look at what we call a giant atom or a large atom. And that's just defined as an atom whose spatial extent now is on the order of a wavelength. And as a result, we can think of the atom being coupled discretely to 2 points that are well separated on a waveguide, for example. And consequently, this dipole approximation or point-like approximation is no longer a very good one. And we need to consider the emission and absorption of these different points, and importantly, the quantum interference that occurs between them. Okay, and that's what the topic of this talk will be about. So with this, I'd like to give an outline. I'll start with waveguide QED and giant artificial atoms. And in practice, that might be the extent of the talk. Let's see how far we get through it. But in case I don't get to these other topics, we've recently demonstrated directional photon emission in this archive paper. And we have done in the past a lot of work on lattices of 9 and 16 qubits and the 3D integration needed to recognize them. But today, I'd really like to focus on waveguide QED and giant artificial atoms. The two leads here were Bharath Kannan, who just recently graduated with a PhD and started a startup company called Atlantic Quantum, and Dan Campbell, who was a postdoc and is now with the Air Force Research Lab in Rome. Okay, so we use superconducting artificial atoms, and I think you may have heard from Josh and Sai this morning about them. Let me just remind you that we're talking about an electrical circuit. Think of it as an LC circuit, resonance circuit, and it is a harmonic oscillator. Harmonic because the potential profile is in fact parabolic. And if we cool down this circuit to a low temperature, where low temperature means that the resonance frequency of the qubit is much larger than the temperature or the energy scale KT, then it's a quantum object. It has discrete energy levels. With excitations, we can count as 0, 1, 2, etc. And the level separation between them is Planck's constant times the resonance frequency of this resonator. Okay, so it's certainly a quantum object or a quantum circuit. but it's not a qubit. And the reason it's not a qubit is because if we try to drive this qubit, even if we prepare it in the ground state, we will resonantly drive 0 to 1, and then 1 to 2, and 2 to 3, etc. And that's not what we want in this case. In the case we heard from Steve before, maybe that's what we want. But in this case, that's not what we want. We want to uniquely identify a 0-1 transition. So to do that, we need something nonlinear. And the nonlinear object we use is a Josephson junction. And that is two superconducting leaves separated by a thin insulator. So think aluminum, aluminum oxide, and aluminum. And this is a Josephson tunnel junction. The current and voltage relation for this tunnel junction are given here, and I won't talk about them in more detail, other than to say that if you combine them in the usual way to define an inductance, then what you find is that inductance is highly nonlinear in the current that flows through the junction. And in fact, if you work out what the potential profile is, it is now a cosine rather than harmonic. And so we would say that it is an anharmonic or not harmonic potential. So in fact, the transmon qubit is exactly this configuration. It's an LC circuit where the L is now a nonlinear inductor realized by a Josephson junction. And so consequently, rather than this parabolic profile, we have in blue this cosine potential. And an important consequence is that the 0-1 transition frequency is now distinct, different than the 1-2 and the 2-3, etc. And so now we can draw a box around 0 and 1 and say that is our qubit. So we'll be using a type of superconducting qubit called the transmon with a slight modification that I'll show you in just a moment. Okay. So there are many, many artificial atoms that we can build from this concept, but all of them boil down to this basic idea. Okay, so now let's compare two architectures. One is cavity QED architecture. This is the most commonly used today with superconducting qubits. Basically, the qubit is embedded inside a cavity, and that protects it from the continuum of modes of the environment out here, let's say. Now, the atom or qubit can exchange energy with the modes in the cavity. And it can also relax. And what we want is for the atom to exchange energy with the cavity very rapidly, much more rapidly than it decays non-radiatively. And then, of course, this cavity also can decay to its environment. But the point is that we've done this because if we put a qubit just in an open environment, it'll decay very rapidly because of all of the modes in the environment. So by putting it into a cavity, we form a few discrete modes. And if we detune the qubit from any one of those modes, in a sense, there's no mode to emit to, or at least to first order. So the cavity protects the qubit in this way. Okay, and this has been used to both control and to read out qubits now for well over a decade. On the other hand, there may be some advantages to taking a step back and going back to a waveguide. And maybe the motivation for me is that we'd like to release and absorb quantum information between different nodes. We might call that a quantum interconnect. And to do that, the cavity becomes an inhibitor because the cavity blocks photons from getting out. Of course, they will eventually leak out, but we'd like them to move quickly from one place to another. Of course, we can also study dissipative phenomena and things like that, because the problem with this approach, and the reason we went to cavity QED many years ago, is there's always on dissipation, right? There's a tunable coupling to the environment, or sorry, there's a coupling to the environment because there's many, many modes in here, right? And the question is, can we create a tunable coupling so that we can essentially decouple qubits from the environment when we don't want them to relax so quickly? And then the second question is, can we engineer interactions that are mediated by this waveguide, right? And of course, the answer to this will be yes, and it's mediated by the this giant artificial atom. Let me just state that there has been a lot of work over the past 12 years in waveguide QED with superconducting qubits, also microwave quantum optics. And I won't highlight or walk through all of these explicitly, but starting back at NEC, Oleg Astafiev and collaborators showing that we can enter the strong coupling regime of waveguide QED. And since then, a number of important works at ETH, University of Waterloo, Caltech and elsewhere have shown that we can operate qubits in this regime. And of course, we stand on these shoulders. Now, getting a little more detail, we have qubits, maybe more than one, coupled to this 50 ohm waveguide. And each qubit exchanges energy with the waveguide at a rate we'll call gamma, right? And of course, the qubit could relax and lose its energy very quickly that way. Now, the qubit can also relax to other degrees of freedom. We might lump that in as non-radiative decay. And those could be things like defects in the substrate on which we build or fabricate these qubits, okay? We'd like this gamma to be much larger than, of course, this non-radiative decay. A circuit schematic would look like this. Here are the transmons coupled capacitively to the qubit, or to the waveguide, which is a 50 ohm waveguide. And now you can see the one difference. This transmon is now called a split junction transmon. We form a squid, so two junctions in a loop with a shunting capacitor. And by putting a magnetic field through this squid, we can actually tune the 0-1 transition frequency in situ. That's a very useful knob to have. But that's the only difference compared to the transmon we saw before. Okay. And then what we'll do is we'll send energy in and out via in this waveguide and see how the qubits react to it. This is a picture of what the qubit looks like. Looking down from the top, here's a qubit. This is a capacitor pad to ground, so it's a lateral capacitor. Here's the waveguide that it's coupled to, and it's capacitively coupled to that waveguide. We have a control line here, which we can use to drive transitions in the qubit. And then we have an antenna here, which is used to tune the 0-1 frequency. And you can see that here. We put a current down the center spine, which splits symmetrically. But because the qubit is over towards one side, that current will induce a magnetic field through the loop, which tunes the frequency of the qubit. Okay. So if we couple atoms to propagating photons, let's take a step back and just think in free space, 3 dimensions. We have basically a plane wave field, and that field hits this very small, relatively small atom. It puts it into its excited state. And when it emits, it will emit spherically. Okay, so immediately we see that there's a mode mismatch between the plane wave that comes in and the spherical wave that goes out. Okay, we also notice that this, if it's a natural atom in particular, it's a very small scattering cross section. Now, 1D waveguides afford us that the light is confined to one dimension, and so this overlap can be very strong. And in fact, the light that comes in to excite the qubit is in the same one-dimensional direction as when the qubit emits it. So the qubit will emit it either backwards or forwards, but that's it, right? And if we think about quantum interference that occurs in free space, you get this beautiful but fairly complicated pattern due to the plane wave and its overlap with the spherical waves. But in a 1D waveguide, it's very simple. If we excite this qubit at a slow rate, less than 1 photon on average, then what happens is when the qubit emits the radiation, the forward-going wave destructively interferes with the original wave we sent in, and it constructively interferes in the backwards direction. So as a result, there's a total internal reflection in this waveguide due to this interference. Now, we often talk about cooperativity, and that's generally in a cavity case. So there's a cavity enhancement as well as electromagnetic field enhancement. But here, we don't have the cavity. And so it's very difficult to achieve these kinds of experiments, say with natural atoms, without the cavity enhancement and the circulating field in a cavity. Here, we just get one for that enhancement. And so we rely entirely on the electromagnetic field overlap. But again, with artificial atoms, this can be relatively large. And so this works. The one requirement, of course, as I mentioned before, is we want the qubit to interact with the waveguide at a rate that's very fast compared with the non-radiative decay. Okay. So with spectroscopy, we can use a network analyzer to send in a very small tone, so on average, much less than 1 photon, and then monitor what comes out the other side. And ideally, in this low excitation limit, we don't expect anything to come out, right? Because we expect everything to be reflected. And that is indeed what we see in experiment. when we tune the frequency, right, we tune the frequency of the radiation coming in until it's on resonance. We'll call on resonance 0 detuning from the qubit. And when it's on resonance, less than 10 to the minus 4 of the input power actually goes to the output, right? We can expand that into a 2D plot of detuning and also the probe power. So more photons as we increase the power. And if we take a slice at 0 detuning as a function of that probe power, we see that when we're in the limit of much less than 1 photon at a time, this destructive interference and constructive reflection is nearly perfect. But what happens is when we get more and more photons in there, of course, 1 photon gets absorbed and re-emitted, but during that process, a whole bunch of additional photons just keep going. And that's why we see eventually that in the larger excitation limit, we do get photons at the output. Okay, so hopefully that's clear. So some single channel measurements, what I want to emphasize here is that we measure in the X basis. What that means is on the Bloch sphere, you can think of, we excite the qubit along X on the equator, and we create a superposition state. And when the qubit emits that photon to the resonator, of course, it is also in a superposition state. And when we measure its amplitude at room temperature using standard in-phase quadrature detection, we get this oscillation and decay function. Now, the reason I mention this is usually we'll measure qubits along the Z basis or in the Z axis with excited and ground state. But if we put the qubit in its excited state, it will emit a Fock state, a single photon Fock state to the resonator. And we know that that is isotropic or symmetric in the IQ plane. And when we measure that, we'll basically average out to 0. We don't measure anything. And so it's a detailed but important one that we will measure in this X basis. We also multiply the voltage signal we measure by a windowing function, and this allows us to extract the signal that we desire. Now, of course, there is noise, and I won't have a chance to talk about it today, but noise that also adds to this very small signal, and we need to calibrate that added noise very carefully so we can remove it when we do our final measurements. And if you would like to learn more about how these measurements are done, these 2 articles from Christopher Eichler and ETH, Andreas Wallerhoff's group, give a great overview of that. Okay. So one more piece of physics is waveguide mediated interactions. We would like to couple qubits along a waveguide. And of course, there are real photons where the qubit just emits a photon at its frequency. But there are many more virtual photons, and that's when the qubit emits maybe close to its frequency, but not exactly. And those photons can be emitted and then reabsorbed by another qubit if the time frequency uncertainty is satisfied, that we do it in a short amount of time or sufficiently short amount of time that we satisfy time frequency uncertainty. Okay, and that leads to an exchange interaction G in principle. Now, what I want to emphasize here is that the separation between the qubits matters. So, for example, if qubits are separated by, say, a wavelength, and we know that the coupling between them goes as the individual coupling of each qubit divided by the detuning, then what we see is that let's take a pair of photons, one that's positively detuned, one that's negatively detuned from the qubit by the same amount, symmetrically detuned. 2 photons. One is negative detuning, one is positive detuning. All the other couplings are positive. When we calculate the net contribution to the exchange interaction, one is negative, one is positive, they exactly cancel. And in fact, that's true for every pair of virtual photons that we have when the 2 qubits are separated by lambda. Okay. On the other hand, we could separate them by a different distance, say 3/4 of a wavelength. And now the story is similar, but we get constructive interference. And the reason is that while we still have plus and minus detuning for this 2 photons we're talking about, let's say, one of the couplings comes in with a minus sign, the red one here, because where it appears at the wavelength, where it appears at the second qubit is negative. Whereas for the blue detuned one, it's positive. So there's another minus sign. Now both contributions are positive for every pair of symmetrically detuned photons, and this adds up to a net waveguide mediated interaction. The strength of that net interaction goes as gamma over 2, where gamma is the rate at which the qubits individually talk to the waveguide, times sine phi, where phi is the phase associated with this distance. Okay, and it's shown here. Okay. So the first device I'd like to introduce is this one here. We have two qubits, qubit A and B. Each one is connected at 2 points, so it's a giant atom, and they're braided, as you see. Separations are being kept equal here. The chip looks like this. We have 2 qubits. Those are yellow, and the blue waveguide meanders back and forth between those 2 qubits. Okay. Yes, thank you. If we zoom in on this qubit here, you can see where the waveguide couples at 2 points. You can see our ability to tune it. And then we use a standard cavity QED readout. This is just an experimental check for us. Good. So we can tune the dissipation. If we have qubit A and qubit B, we're going to detune B so we just don't see it. And remember that we had a distance phi between this point and qubit B, and then a second phi back to qubit A. So the round trip of A to itself is 2 phi. Okay. And depending on this value of phi, which we can tune by tuning the qubit's A frequency, we can get either destructive or constructive interference. And that manifests itself, for example, in its decay time. So if we look at this particular frequency right here, now what I'm plotting here is the decay rate, 1 over T1, we can see that the decay rate is very, very low. Okay, that corresponds in this upper plot to this decay time of about 32 microseconds. This is the frequency where our interference is such that the qubit will not emit the photon to its environment, right? There's a destructive interference to emit to the photon to the environment. Now, what that means is that the only decoherence mechanism we have left is, say, to the substrate or to local defects, but it is not emitting to the waveguide. So we've decoupled the qubit from the waveguide just by engineering. On the other hand, if we change the qubit's frequency more and more, we can see that the decay rate increases, or equivalently, the decay time decreases. Okay, so we can basically eliminate this term to the waveguide and be left with just the non-radiative decay rate by engineering. So we can decouple a qubit from the waveguide. We can also interact qubits along the waveguide. So now we have 2 qubits, qubit A and B. And again, these are each phi separated. And so we can recognize these different points between A and B. And so the coupling between them, as I explained, is given by gamma over 2 sine phi for each one of these pairs. And there's one more pair, the outermost points, and they couple to each other, now separated by 3 phi. And of course, this is a coherent process, so the net coupling will be all of these added together. And when we take one qubit, say qubit B, and then we tune the other qubit's frequency from off resonance here onto resonance and then off resonance again, we see that an avoided crossing opens when they're on resonance. And this indicates that the 2 qubits are in fact talking with each other, or they're coupled with a strength G. And what's very interesting is that we can have a non-zero coupling between these qubits, while at the same time, each qubit individually is decoupled from its 50 ohm environment, the decoherence-free frequency. So we can have decoherence-free interactions via a waveguide. Now, I want to emphasize decoherence-free means from the waveguide. We still have all of the other non-radiative decay channels. But the dominant one here by far is the waveguide, and we've turned it off. Okay, so now we can engineer coupling spectra with giant artificial atoms. Let me just mention there are a number of knobs we can turn. One is the number of coupling points. We've talked about 2, and when we couple at 2 points, we have one decoherence-free point in 0 to 2 pi. But if we increase the number to, say, 3 connections to the waveguide, we can now have 2 unique points where we have decoupling. N equals 4 would give us 3, etc. There's always n minus 1. The second thing we can tune is the relative coupling strength. So if we have 3 points that we couple the qubit to the waveguide, we can change, say, one with respect to the other 2, right? And here it's 0.5. But when we increase it, you can see that the region that is decoherence-free expands. The minima come closer together, but this potential well, if you want to think of it that way, or barrier gets smaller and smaller. And then the third is, of course, the distance between the qubits. We've already talked about that one. So there's plenty of opportunity here to engineer the system. So in the experiment I'd like to talk about now, where we demonstrate all of these together, this is an n=3 giant atom experiment, where each atom is coupled at 3 points to the waveguide. B is as well, and we've braided or interleaved the couplings. And now the way that this looks is if we have the waveguide coupling back and forth between the qubits. Each qubit is coupled to the waveguide 3 times, right? And the values that you see here, phi1, phi2, phi3, phi1 and phi3 are about the same, half of phi2. And the coupling gamma 2 is about 4 times gamma 1. That's what we chose for this experiment. And when we do that and characterize it, what we see is that in blue is the decay rate. And because we couple at 3 points, indeed, we do see 2 decoherence-free frequencies, one at around 4.5 gigahertz, one at around 5.2 gigahertz. And when we bias the 2 qubits together on resonance, we see that they have this profile for the coupling that we expect. But importantly, at the decoherence-free frequencies, we get a little over 0.5 megahertz of coupling for this particular design. Okay. So the experiment we did is we started with 2 qubits, A and B, each one biased in their own decoherence-free subspace or frequency. What that means is that they're off resonance and they don't couple to each other, right? So they're not interacting, but they're both protected from their environment. We then put qubit B in its excited state, and then we take qubit A and we shift its frequency to be on resonance with qubit B. So now both qubits are at this decoherence-free frequency and protected, but they interact with each other for some period of time, tau. We then put qubit A back in its original spot, so it's protected but not interacting anymore. And then we do the readout. This is what the result looks like, and you can see these, chevron patterns that are pretty standard for this type of swap interaction. If we look at the on-resonance case, you see that qubits A and B exchange energy with one another. We're just plotting the excited state here. And if we pick the point right here where the 0.5 point, this is in fact an I-swap operation and leads to this entangled state 0,1 minus I10, the I from the I-swap. And if we then do tomography, what we see is that we have done this with a fidelity, the state fidelity of about 94%. Now, that's not a world record by any stretch, but I want to emphasize that we did this, we prepared the state, we did all of these operations while the qubits were coupled to a 50-ohm waveguide. Now, we did some tricks to prevent it from decaying to that open environment, but the entire time the environment was open and they're ready to accept energy. So in that sense, this is quite a remarkable number, and we've improved it since then. So what this says is we can entangle qubits despite the strong coupling to the open environment. All right. Now, what that leads to is an engineering connectivity with waveguides. And I just would like to mention a few experiments. These are figures from Anton's paper from 2018, where you can have an Ising spin chain of nearest neighbor interactions. You can then braid it with giant artificial atoms. You can have a geometry like this and even have all-to-all interactions if you can do crossovers, which we're able to do in our lab. So there's a number of experiments that we can do now that we have this open environment. And I realize I'm coming to the end of my time, so what I would like to do is just highlight very quickly directional photon emission experiment. Let me just show you the device and the result, and I'd encourage you, if you're interested, to look at this archive paper. This is also by Barath, but in collaboration with Aziza, who's a graduate student in the group. And let me just say the motivation. We want to move towards quantum interconnects, right? And that means qubit processors on chips may not be monolithic. There may be many distributed chips, and we need to connect them with a waveguide. To date, that is generally done with cavities. Cavities have high fidelity, and they are bidirectional. You can send information in both directions, but the number of qubits we can attach to cavities is somewhat limited, and that's limited by the frequency we want of the cavity, what we call free spectral range. There was a nice experiment at ETH where they coupled two refrigerators together with a meter-ish long tube, and that's also possible. But this is a waveguide, but it's a single-ended waveguide because they needed to have this non-reciprocal element in the middle. So you could send photons from the left to the right, but not from the right to the left. And what we would like to do, and we've taken the first step there, is go to bidirectional communication with itinerant photons along a waveguide, where you would have modules coupled to this waveguide and send a photon left or right, depending on which modules you want to connect. And this is an ideal platform for us because we can couple our artificial atoms to this waveguide. And step one is going to then be, can we emit a photon to the left or to the right on demand, which we've done. Step two, which we're currently doing, is can we then receive that photon downstream? Now, in the interest of time, I won't have time to talk through this in its entirety. Please reference the paper. But what I would like to say is that we do this by creating an entangled state of 2 qubits, and the entangled state has a phase, and that phase is pi/2. And when that phase is positive, the rightward going photons emitted from these two positions constructively interfere, whereas the leftward ones destructively interfere. On the other hand, if we put this 2 qubits in an entangled state with a negative pi/2 phase, now the leftward going photons constructively interfere, but the rightward photons do not. So we can send the photon left or right just by setting this phase. The emitter module looks like this. It's a 4-qubit construction with 4 tunable couplers. And the idea is that qubits 3 and 4 are where we create the entangled state we want to generate to create a left or right going photon. We then shuttle that state down to qubits 1 and 2, where they emit it to the environment, right? And in the future, qubits 3 and 4 would couple to a processor. So this is an emitter module. Okay. So we did this experiment. I'm just showing the shuttling. Here's the results. We can emit the photon to the right with a positive pi/2 and 0 to the left, and vice versa if we have a negative pi/2. And we can do this with, let me just show the tomography results. We do this with about 97% to 98% fidelity, so things are getting a little bit better. So I realize that was very fast, but I want to emphasize that this step is done. And the next step that we want to do is receive the photon. And so the idea is that you could have multiple photons on a waveguide. One of them emits the photon. We detune these two that are shaded. We want to collect the photon here. And the very nice feature of this is that the same module run in a time reverse fashion will capture that photon. Right, and so we can capture the photon here and then connect to a quantum processor unit upstream. So that's what we're working on right now. I mentioned, or I showed it earlier, but I didn't mention it words, that this very nice module scheme was developed by Yasu Nakamura and his colleagues at the University of Tokyo. With that, I'm afraid I'm out of time. I won't be able to talk about lattices or 3D integration, but let me advance now to my last slide so that I can recognize the people who actually do this work. Oops, that's not what I wanted to do. Let me bring it over here. There we go. Yes, that's what I wanted to do. There we go. So this, of course, is an effort by many people, both the Engineering Quantum Systems group at MIT and also at MIT Lincoln Laboratory. And of course, we have many US government sponsors. And so with that, I'd like to thank you for your attention, and I would welcome any questions.
Thank you very much, Prof. Oliver. Prof. Franco, are you there?
Yeah. Well, thank you very much for a great talk. And then are there any questions? Let me see here in the chat here. And then Okay, the last part went a bit too fast. So therefore, if you don't mind, because there was this exciting results on lattices. So if you don't mind just spending a couple of minutes on the exciting stuff that was like a rushed at the end.
Yeah, well, I didn't even talk, rushed to the point where I didn't even talk about it, but let me do that, and I'll just highlight these results. So the point here is that, there we go. You know, we've done some experiments in the past with 5 qubits in a linear chain, and our state, you know, the best that we've got now are about 99.95% single qubit fidelity, almost 3/9 2-qubit fidelity. And we're currently doing experiments on lattices like this, but you can already see that things are getting quite crowded in terms of trying to bring the signals in and out of there. And so we know we're going to need to go to 3D integration. With a 3x3 array, the last chip we measured, we did what's called a random walk. And basically you create an excitation in the left corner, and you see how it goes to the upper right corner in steps. So this would be 1 step, 2 steps, 3 steps. And when we do that, you can see the excitation basically go from the left corner to the right corner and back and forth and back and forth. And that's an experiment. This is the simulation, and they match very well. This is an example of a Bose-Hubbard model, which we can realize naturally with these capacitively coupled qubits. The qubit is the on-site interaction. The anharmonicity is the interaction strength U, and the coupling between qubits is the J. And this is in the so-called hardcore limit where U is much greater than J. So we've done a number of experiments, but the ones that I'd like to highlight right now are localization. And the advantage is that we can tune every single qubit, you know, and of course set them in random configurations to emulate randomness or disorder. So in a disordered lattice, we can see Anderson localization both in 1D, we just use the edge qubits, or in 2D if we use all 9 qubits, for example. And, you know, simulation matches theory and data. We've also done Wannier-Stark type localization where you put a constant field or a gradient across. And in 1 dimension and in 2, here's the 1-dimensional results. And you can see these block oscillations, as they call it. Here we're exciting 2, and 2 tries to go to 1 and 3, but due to the gradient, the excitation comes back to 2, and that repeats over and over and over again. And again, we've done it in 2 dimensions as well, where you
Will, I think your sound got temporarily
can have
off.
2 different, that's just 2. I'm sorry, what's that?
Your sound got temporarily cut off.
Oh, am I back again?
Yeah.
I see. I'm sorry about that. I don't know where I left off, but
Essentially on the Wannier-Stark ladder, you see block oscillations in 1D and in 2D.
yes, that's right. That's right. And that's what we're showing here, is that with a gradient applied in different directions, can be the same or different, we can get block oscillations in 2D. So,
can you implement the SSH model on these kind of lattices?
well, possibly. So I think that this is, you know, what we do next are we're thinking about, you know, these type of models as well as some topological models that we can do in 2D with a lattice array. And we'd like to get a little bit bigger. So we're currently at 16, and then I think the next step will be a 5x5 array. And of course, to do that, we need 3D integration. And I won't talk about that because I realize I must be getting out of time at this point. But the idea is that because there are so many lines that need to come in and address these qubits, it just won't work anymore as we get larger and larger to come in laterally. We have to come in from the 3rd dimension. And so we can take a chip like this and we flip it over onto other chips. And those other chips serve to route the signals and then bring them up to the qubit that we want to address or to read out. And so because we're coming in from the 3rd dimension, we call it 3D integration.
Mm-hmm.
Yep.
Let me see here. There is in the chat room, there is some questions here. One question is, how is fidelity defined? But I think this is probably this, you're using the standard definition of fidelity, no?
Yeah, that's right. So there's, of course, state fidelity and process fidelity. In the case of the photon state tomography, that is a state tomography that we did. In the case of the qubit numbers that I quoted, those were interleaved randomized benchmarking numbers for the gate. So that would be a process fidelity.
Another question by Wei Chin is it possible to get a gain atom model in cavity in addition to waveguide? Let me see if I understand it. Is it possible to get a gain atom model in a cavity in addition to waveguide?
I think you meant a giant atom cavity, atom model.
Ah, giant. Okay, so okay, sorry, this is a typo. Is it possible to get a giant atom model in a cavity in addition to waveguide?
Yes, it is. And in fact, I'd like to call out some work that was done by Vijay in India, where he basically did this. He made a ring of qubits on a waveguide, which effectively is a ring, you can think of it as a ring resonator, and showed that, you know, depending on how he oriented the qubits around this ring, you know, he got different types of constructive and destructive interference. And so I think, you know, the answer is yes, that you can certainly couple qubits in this manner and get this constructive and destructive interference.
Any questions from the audience there? Like take a microphone or raise your hand or.
I think we're good.
The 3D the 3D part, I assume, will be hard. No, is it like near term, or is like we're talking about 1 year from now or 2 years, the 3D electronics, or is it already
No,
working?
in fact, our 16 qubit chip is flip chipped, so it is in the 3D geometry already. So this picture is not, but you know, after trying to measure this guy, it worked, but we know that these long wire bonds are problematic. So the next device that we measured, which is the one currently in the fridge, is a flip chipped version of that. And through this IARPA quantum enhanced optimization program, we also have quantum annealing devices which utilize all 3 layers. So this is contemporary.
So I have a simple question. The picture you showed before, the last one with the device, approximately how much does it cost? Like, yeah.
You mean money?
Yes, yes.
Oh, the cost to fabricate it? Hard to say. Hard for me to say.
Do you think they can donate one to us in Africa? Oh, well, in Kigali.
Yeah, so, you know, the tool set that we use to do this, of course, has been procured over many years, and I certainly don't own them myself. It's part of a shared use facility. And, you know, I would guess that those tools, you know, would run altogether, that type of facility would probably be 10 million or several tens of millions of dollars to, but of course that facility can do much more than just make these types of devices. So I think there is a, you know, there is a facility that one needs to be able to do it, but then that cost per unit comes down substantially if you can get that facility running.
Okay, thank you very much.
One time, it's an infrastructure or one-time investment, yeah.
Do you have any plans to essentially to transform virtual photons into real photons? I've been able to detect them with this device. You're talking about this virtual to real transitions like dynamic Casimir effect. Is this possible that could be studied in these devices here also? Like,
well, that's a good question, Franco. I haven't really thought about it, but you know, maybe that's another area we can work together on.
especially if it is an ultra strong coupling limit, then you have the terms beyond the rotating wave approximation, where like in the lamp shift, you can actually you can actually borrow photons from the vacuum, or you can actually donate photons from the vacuum. So there are these higher order perturbative effects that Anton and my collaborators here, Savastano, have been working for years. And it's very, very exciting possibilities that go beyond because if you look at the evolution of the field, if you like step back at the big forest, there is, Harosh and Jean-Michel Raymond did this great work on this weak coupling, and then becomes strong coupling, and then there is circuit QD and these great things. When you go to stronger and stronger, you're probing a different field, and this is what LAMP was doing. Essentially, the LAMP shift, the shift was seen there because you can actually access terms beyond the rotative approximation. So therefore, there are like anomalies. There is exciting things happening, and then and the possibility to break up essentially these pairs in a more controlled manner, because right now the electronics is getting faster, the controls are getting better. But this is something we can talk some other day, and then this is an exciting frontier for exploration. Also, we can talk to Anton, was here a few weeks ago. This we're discussing with him also. So
yeah, no, that sounds good. I think, we've basically shown a platform, I think, at this point. Now it's interesting to ask, what can we do with it, for sure.